So now we're actually getting to some of the equations for circular motion. And the first thing we need to do is write the momentum as magnitude times unit vector. And this way, when we go ahead and look at the derivative dp dt, we see that we've got these two terms, and we're going to have to take the derivative of each one in turn. So looking at the derivative of this first guy right here, we get d magnitude of p dt times the unit vector plus the magnitude of p times dp hat dt. Now, this term right here is actually pointing in the same direction as the momentum, because all of the directional information is contained in that unit vector. So this component is what we'll call dp dt parallel. It's parallel to the direction of the momentum along the direction, which means that this component right here is going to have to be perpendicular. So this is what we will call dp dt perpendicular. And if we go ahead and take a look at, say, we've got an object that is not only changing direction, but changing the magnitude of the momentum. Let's say in this case we've got p initial is this way, p final is this way, here's our delta p. If we go ahead and break this delta p up into a component that is parallel and perpendicular to the original direction. Okay, so this is essentially our coordinate axis here. So this is the component that's parallel to p initial. This is the component that's perpendicular. So the parallel component has the effect of speeding it up or slowing it down. In other words, this component right here is responsible for the rate of change of the magnitude. This component is what causes it to turn. That's responsible for the rate of change of direction. So let's just write that again, that this right here is the rate of change of the magnitude of momentum. Or another way of thinking of that is it tells us whether or not it speeds up or slow down. This is the rate of change of direction of momentum. This is telling us how it's turning. And they go through derivation in here. I'm not going to focus on that. But essentially this component right here, this rate of change of the direction, the dp dt perpendicular, can be written as this equation here, p times v over r, or if we write this out in terms of mass and velocity, this is also equal to gamma m v squared over r. So this is our dp dt perpendicular. Now, one thing I want to point out that this is not actually a force. dp dt itself is not a force. Now, it's related to the force, but the thing to keep in mind is that it's the force that causes dp dt, not the other way around. So really, when we write F net equals dp dt, in some sense you might argue that it should be F net causes dp dt. And but frequently what we do is we end up calculating what the net force needs to be to give us a certain dp dt. But don't think that dp dt causes the force. It's the force causing that change in momentum. So another thing to think about is that this dp dt perpendicular, and actually the equation is a magnitude, is gamma m v squared over r. This is not a force, okay? This is not a force. What this is telling us is how large does this force need to be in order for the object to move with this velocity and this radius. Okay, let me say that one more time. This equation tells us how large a force we need to apply in order to get something to move with a given velocity and a given radius. So this right here is not a separate force. This is never something you would put separately on your free body diagram. This is frequently referred to as the centripetal force equation, but you need to be careful because this isn't necessarily the centripetal force. Centripetal force is actually a particular force on the free body diagram. So let's take a look at this example on page 199 of a bucket on a string that's going in a vertical loop. And in this case, the centripetal force is actually caused by the rope. Okay? The centripetal force is caused by the rope. And if we want to know what magnitude it needs to have in order for this thing to move in a perfect circle, then we would use that equation gamma mv squared over r to figure out what that needs to be. However, it's possible that this force has a larger value or a smaller value, in which case this thing would move in a circle with a different radius. So let's go ahead and I want to walk you through this example. And here I set up my sketch. My system is the bucket plus the water. The surroundings is the earth and the rope. And we draw our free body diagram. We've got the tension. Okay, and I really want to emphasize that this force right here is what we would call the centripetal. I apologize for the writing. That is the centripetal force. It's the force pointing towards the center of the circle, or is providing the centripetal force. There's an additional force of the gravitational force on the bucket by the earth, and when you add these two together, you get a net downward and leftward force. So I've written out my knowns, my assumptions, and my strategy is, first, I'm going to find the components of the net force that are parallel to P to find this dp dt parallel, and that will take care of the first part of the problem. The second part of the problem then is using gamma mv squared over r to find the tension force. So usually you'll be given some information. It'll either be kind of obvious what the parallel components are, or you'll be given some angles that you can figure out. In this case, since the direction of motion is this way, F net parallel is just the forces in this direction, and looking at the free body diagram, we see that that's just the downward force of gravity. This is just equal to mg. So dp dt parallel, if we go ahead and put this in vector notation, is equal to 0, comma, negative mg, comma, 0. Now, to find the tension force, what we're saying is we have a circle with a known radius and a known velocity, and so if the tension force is just right so that it sends that bucket through that circle, and it's going to be approximately the mass of the bucket times the velocity of the bucket squared over that radius. And we can go ahead and plug in our results, and if we want to go ahead and check that this makes sense, well, we expect the downward force to just be gravity, due to gravity, I should say. So that really kind of corroborates that one. This one right here, if we were going to go ahead and plug the numbers in, we get something that's about 202.5 newtons. I'm just going to call that around 200 newtons. mg, we should note, is about 3 times 10, or about 30 newtons. This is approximately 0, negative 30, 0 newtons. So this force is a little bit larger than I would have expected. It's about 7 or 8 times larger. But when you consider that this is a bucket moving pretty quickly, I guess that's not an unreasonable number.